used or not enough used in our food industry. The message that I want to give you today is that this approach to calculations, number one, it's the calculation we've always done. The main difference will be that our uncertainty about our models and the variability that we are in the data will be in our model will be incorporated in our calculation to get a better handle to the confidence that we have in our calculation. Our recommendation with the creation of a product, process condition, a shelf life, packaging film for food product, we always have the risk that our recommendation may not produce a result that we expect. So that this can be used whether it's a high pressure process application, a shelf life estimation, FD, juice pasteurization, everything that you will encounter in your professional life. So, before going into the topic, let's tell a bit about myself. I'm originally from Chile, and if you were to look outside my window, you will see that I'm in Oregon. In Oregon, it rains. And today, not from other days, it's raining. So I wish I was today back home, and you can see in this slide beautiful beaches of my hometown, which I would really like to be there today. In Oregon, and the rain is good. We have then a summer which is beautiful to enjoy. So please get yourself invited to visit me here in Oregon anytime. Okay, into the subject matter for today's presentation. Need probabilistic engineering approach. We should really work in the real world, which is aboundant with certainty and variability of information. So how we've done it in the past. Take, for example, the case of summer processing. Typically, the process would be designed using mean values. After we finish our calculation, we'll use some design correction factors. It's a product failure risk. And the question is that how do we select that correction factor to be representative of the risk failure? Approach used often is to use extreme values. So what would be the worst microbial load, the most resistant microorganism? Always looking for those extreme values and use them in design. And becomes what's the probability that that extreme combination of factors would occur. And since we're still not confident after using even extreme values, and we still add some correction factor, one can probably guess that we are using a lot of over-processing in our food safety approach. Is that government agencies, they impose regulations. In order to impose those regulations, use national data. So they take the whole country or the world and they find what situation the whole world to decide how food should be handled and make it safe for the consumer. This national situation may not, and for certainly most likely does not, represent the situation of individual processes. So the processor makes an attempt to reduce initial load by improved sanitation technology. She may not benefit from the effort. Another example could be a shelf life study. Typically, those are conducted as some accelerated laboratory conditions. And we've seen many times that they fail to predict because the consumer of different production batches expose different farm to table conditions. We had a good example of a company in Mexico who had done a beautiful study to determine the shelf life of the product. They also conducted a beautiful market analysis to determine which was the exact amount of time that would be required to reach the consumer of the product. So that market study, they realized that they needed at least 35 days shelf life for their fresh cheese that they were trying to distribute. And the consumer with a product in good quality. So shelf life studies were done to adjust process conditions and formulation, etc. To ensure that 35 days were possible. They implemented all the changes. They found that a large fraction of the product being returned to them because it was not meeting the 35 days. The reason is mentioned in this seminar today, the variability of the data. Impossible to state a laboratory condition if all the factors with the shelf life of a product from its action, distribution, and handling the condition. So when they go into the real market, all the steps that are required to bring something from the farm to the final consumer, all steps have variability, and therefore they will affect shelf life. We developed for them a shelf prediction system based on probabilistic engineering. We're able to help them in order to solve the problem. Since emerging technologies is one of my research interests, when you remember that these emerging technologies must use a minimum processing time differentially viable. In the case of thermal processing, where you used to add additional processing time, we feel uncertain about the safety of our product, but we cannot afford with alternative processing technologies. They have a high cost, and therefore we must minimize the processing time to make them actually viable. Time for this processing technology, we consumer that them as preferred the product because they are perceived as when they receive a minimum cost. So they are trying to minimize the processing effect on our product to attract these consumers seeking for minimally processed food. We don't want to use excessive processing time. So we have to be really careful in selecting those processing conditions so that they are to produce a safety desired or the stability desired, and so minimum because we want to use the processing cost. So next slide, slide 4 now. Basic engineering, and in this case, we're going to be using a couple of strategies. Vinicio was at the beginning of the presentation. The couple of methods are used to analyze method where you have many data set of data, and them following different statistical distribution. So on the right side, we have the 6 here, where on the have all the input data using in our calculation, and some of them can have a normal distribution, can be just a list of values that measured and a line that we achieve in the processing facility, for example, will be measuring their characteristic, microload, etc., to design the process. So we have maybe a year worth of data, and those is this column of data that I'm showing here. Okay, could it be uniform distribution or any form of statistical distribution that may describe the variability of the data that will be used in our calculation. So then, what we will do in this Monte Carlo strategy is that we will be simulating the variability of the parameters will be used in our calculation. Either the statistical distribution to select them, or just select them randomly from a list if we choose to describe the variability as a set. There are calculations for each of set of data. So each iteration will just use the same calculation we've always done. It would be that after we finish one calculation set, some kind of an output value, we'll another iteration. So a sufficient number of iterations will get not a single value for output data by statistical distribution, which should be analyzed to make a decision about what should be the process condition, the packaging, the shelf life of the product. You will see that this approach would be fairly generic. Yeah, so about the number of data sets they will use, or the number of iterations it will be used in our calculation. From your statistics courses way back then, if we have a statistical distribution, maybe have a normal distribution, for example, and we know the mean and standard deviation for that normal distribution. I can draw 10 values randomly and on a histogram. And when I have 10 draws, my histogram, that's very much like a distribution. If I increase to 100 draws, 100 replication of that process of simulating the normal distribution, we can see that it begins to approach. In 1%, it's very good. In 10,000, you really don't have much of an improvement. So there's somewhere between 1,000 and 1,000, you have more than enough. What is that? We use the coefficient of variation. So the ratio between the standard deviation and the mean for that simulation of the data. So we see a plot of the coefficient of variation, and you can see the sampling size. So 0, 500, 1,000 values, and the CV for different parameters in our output calculations. The particular example they were using was used to simulate the of raw oysters. So nice from farm to table handling, and we had different load estimations along the process from the farm to the final consumer. And where the CV at the beginning is quite noisy, as we increase to about 300 in this case, or 400 in this case, the noise begins to decrease, in between 500 and 1000, it becomes fairly stable. So here that if we choose a sample in size of 1000, it's pretty safe to say that we have a stable coefficient, meaning that we have a sample size for a coefficient size. As I said at the beginning, this risk analysis approach based on Monte Carlo can apply to everything. So I want to try to show you in the next slide this application that we have tried, just a selection of some of them. So let's take sample processing, and let's just assume for simplicity that we're going to believe that first order kinetics is valid. And you know that this assumption of microphone activation as a first order kinetic is not a description, and we have a lot of people, including ourselves, that have been push forward alternative models to the first order kinetic. But for this presentation, let's assume that first order kinetic is that. It's simple, right? We have a certain initial load in 0, then to decrease to a certain lower level n, and let's say we're doing thermal processing of change. The conventional goal is to reach a risk of 10 to the minus 9 force per container. We need to know what is the for the reduction is some constant temperature. Okay. So the process, we are trying to calculate the amount of time that you required to achieve this goal from going from 0 to. So the first, we first define a sterilization value as the log of N0 by N. We calculate the process time. It's just multiplication of the Z value times this D. So from there, just use average values for this calculation. Or some other cases, people have used extreme values. The 1 4 and 10 to the 9 containers, which is means that we used to require about an SD of 12 because we were assuming the initial load N0 was 10 to the 30. Okay, we have this calculation and we're trying to activate close to 9. Assume that we're interested in 12 decimal reduction. We look at our tables of data and we find that the D value 250 Fahrenheit, 8.2, for the process at 250 will be 2.4 minutes. 5.2 equals 2.4. It can be much simpler than that. But we decide to measure this as V values and these D values, and every time we process a batch of food, with how much SD we really need to reach to 10 to the minus 9. So we use those values of SD that we do experimentally. And let's also, since the food composition from batch to batch may change a little bit, and the spores may not be exactly behaving the same as other experiments, and because we all have experimental variability, we obtain in different D values every time we do this determination. Calculation now for these values, we see that we get different values of the processing. So what should I do? That value should I use? So well, let's take one of the worst values or the worst value. whatever you want to do, 3.56 or 3 or 7. And is that good enough? And so to do the experiment, who knows what will obtain in the repetition of the experiment or of the production with another batch. So alternatively, I could use the worst SB value, a worse D value. We'll have a process time of 4.22. Rather than to using the worst value for every possible combination of data, we see that, well, how likely that will be so unlikely that we're going to be facing so many worse situations at the same time. And here I'm just looking at 2 factors, but in reality, you may have many more factors involved in your calculation, and therefore the probability of all of them being in the worst case scenario is a bit unlikely. Likely is not a very good engineering term, and we need to be a little more in our decision rather than saying we believe that this would be good value. So I use the probabilistic engineering approach to solve the same simple thermal processing situation. So the same safety objectives, those things are upon us by some regulator. So we keep 1 in 10 to the 9 container in a process objective. However, keep the same objective. Now we want to add a restriction that the objective must be met with 95% confidence for all production batches. Okay, this is how regulatory worldwide are beginning to work. If we look again to our schematic description of the problem, so now we have an N0, but instead of an N0 value, now we have an N0 distribution. So we've been measuring the load of batches coming to production and have an idea how the N0 varies from batch to batch. Measuring the D value so that we can collecting information how the D value changes with slight changes in the formation of the product, simply because the data is an experimental determination, and the experimental determination will have some variability. And then keeping again the 10 to the minus 9 n, but now when I specify that we want to reach this goal with 95% confidence. Remain the same. The same process objective. And then now we need to deal with the ability of the data. Okay. So now, and the N0 value are not just a single value, but actually a value that has variability, and therefore take random samples of D values, random sample of N0 values, repeat calculation many times to determine which our processing time they should be used or recommended. Do an application. We use pasteurization of milk as our first application. And I want to assume that we are concerned there's a new emergent pathogen showing up in our pasteurized milk. And we would like to know whether pasteurization is doing its inhibition of this microorganism. About 10 years ago, we had a lot of research on this pathogen, Mycobacterium avis, subspecies paratuberculosis, and we about its potential presence in milk in the consumer. Well, this pathogen has been found in cattle and other ruminants. Is called a disease called jaundice disease. It's a disease, the disorder, the absorption of nutrients from the entry point until exit point. Okay? So the cattle is infected with a pathogen, and then its ability to get nutrients from the feed, the farming decrease, and slowly, steadily, the animal becomes weaker and weaker, milk production decreases, and finally the farmer realizes there must be a problem here. Unfortunately, by the time that is detected, it's most likely the entire herd is being contaminated, and the herd of this farmer is contaminated, but also most likely the herd of the neighboring farmers. Treatment is too clear and too lengthy to be of any value for the cattle rancher, and therefore the solution at that point is to destroy the entire herd, and not destroy the entire herd of the farmer, but also the herd of the neighbors. And you can imagine you would not be very popular after this has been detected in your cattle. There's a similar disease called jaundice disease. Again, same problem. Nutrients are not absorbed. Therefore, for some time, there's some suspicious that it could be related to the same pathogen. Should be not the case. But they suspected the involvement of Mycobacterium in Crohn's disease. People started seeing whether the pathogen was present in this patient. The was found. As you can find in the pathogen in a person with a certain disease, not the pathogen is involved. However, the of this pathogen in patients provides the that the surviving pasteurization, the pathogen is surviving pasteurization. Therefore, the pasteurization would need to be recalculated. Now, a probabilistic engineering approach to solve this risk. We should ask is not whether survive pasteurization, but should be expressed as what is the probability that pasteurization goal is met. So if we define the goal of pasteurization as a 5D reduction, which is since the pasteurization of juice regulation was passed a few years ago, let's assume that we have an objective of 5D pasteurization for this pathogen to ensure this bacterium that survive pasteurization. The number of decimal reduction achieved by conventional pasteurization is 71.7 degrees Celsius. Convention. And here with this histogram, we are plotting on the horizontal axis with the number of decimal reduction and the frequency of that event, and now we have the cumulative frequency of that event. The goal is to have at least 5 decimal reductions. here it is all the cases of results from our calculation, meaning that more than 4 decimal reduction achieved per life. So 0 than 3, less than 4, more, less than 3, etc. So if we add all this together, they represent all the cases that are below our goal of 5 decimal reduction. And that would represent 68.4% of all cases calculated. So we calculated 1,000 cases, 68.4 were below 5 decimal reduction. In other words, there's 2/3 probability they're not meeting our goal of 5 decimal reduction. So the problem is simple. We need to increase the severity of our condition. Either increase the time, or we could try a combination of both. Try increasing the time. So how this will look schematically shown, and how the calculation will look in Excel. So log of N0 an experiment. So we have loaded milk with Mycobacterium species paratuberculosis. I call it for short. So the load of map for the milk, and the average was a log of N0 of 7.3 with a standard deviation of 0.6. So using this information, we create 1,000 values. So this is 1 to 1,000 values of the log of N0. We treat the milk through a conventional process. So 71.7 Celsius, 50 seconds. And what are the survivors? So at a log of N of 2.7, with still a standard deviation of 0.6. So then generate 1,000 values of log of N. Calculation would be then the number of SB achieved. So the number of SB achieved is very simple. The difference between log of N0 and log of N. So calculation here and we have 1,000 values of SB, and they give us a mean of 4.59, and this is the deviation. So at least from a mean value, we're achieving 5 decimal reduction. To improve the process. So to calculate the d-value. So very simple, because the d-value is the processing time divided by SV. Time we know is 15 seconds. And value we calculated here 1,000 times. They have now 1,000 estimation of the d-value used in for calculation. So now I know what I'm looking for is processing time by the d-value which I have calculated here 1,000 times, and therefore V. Which goals we have for this V? So what goal could be, I want to sure that at least 5 decimal reduction will achieve. So SD must be larger than 5. Okay. If we try different values of the S value, the processing time, we by error, which time So we'll find that the processing time required will be 20 seconds. Okay. To a different goal, we could say that our goal is to have decimal reductions in those 95% confidence. Again, we use the same formula, week a processing time. You estimated here 1,000 times. To set the distribution by only 5% of them less than the 12 decimal reduction, or 95% of them being above 12 decimal reduction. And now in a different processing time. If you shelf life and look at the shelf life of dry and medium moisture foods, and I will need to have an estimate of the moisture content. I'm going to use a well-known gap equation for estimation of the moisture content. So extent, and that moisture content depends on the water activity of the product. And model parameters M, K, and C, which I must obtain experimentally. Obtain experimentally, there will be some uncertainty about their values. So there will be mean and standard deviation describing that. Value could also be another with because another factor with variability, because the production of my food may always yield the same water activity. So it could produce insert here all the mean and standard deviation for this value. In case I want to assume that they're good at producing this food, and when the water activity has no variability, just for the sheet. For this product, when I use Lapusa's approach, where I is the initial moisture content of the product, and the moisture content of the product when it reaches some critical condition. So let's start with I. Moisture content is reduced to this critical value, and it could represent this moisture content loss, which would represent also a weight loss. And we are losing weight. Product would be at risk of not being in compliance with our label, because if we said that we had 1 kilo in our product and we lost moisture content, our no longer 1 kilo, and we in violation of the labeling law. With the moisture content that product would achieve toward in which the equilibrium with the relative humidity of the storage condition. K over X are the properties describing the packaging material chosen, area, the amount of weight, the weight of the solid in our product, vapor pressure of water at the temperature of storage. So this P0 with the function and with an expression as a function of temperature. So here we could put temperature 1, 2. A slope area of interest. So we are not interested in the behavior here, but only from the area of interest from MI to ME. And that would be the shelf life that I'm trying to estimate. Okay. Parameters could variability. So I could have here K over X. The parents could be values reported by the supplier with a mean standard deviation could also have variability, the weight of solid could also have variability, and temperature could have variability. All of them could be inserted in this calculation. To just the variability of the gap parameter, this is what the shelf life of the product would look like if it's 30 degrees Celsius, about humidity, and the product had an initial water activity of 0.8 in this rate of slice. So for in this packaged material with polyethylene, it range from 37 days to as much as 69 days. Histogram generated, and the red line would be the cumulative frequency for this histogram. Shelf life should I use? You need to decide a confidence level. So I'm assuming that I want to make sure that no more than 5% of my product would fail to reach the target of moisture content at the end of its shelf. So here 5%. Go with the cumulative frequency function. You can see that the shelf life of my product under this storage condition and using polyethylene as the packaging material will be 39 days. The product they will last longer, but there will be a few that will need the 39 days that would account to about 5% of those different batches that I produced. Let's see some of the advantages we've seen so far. First, we can simulate the uncertain variability when formulating, processing, and distributing foods. We have almost always have variability in certain information, but rarely use it. Yeah. So the change is now that the design task we find as a goal to achieve with the variability. So I'll give you an example. We can say the goal is 5D pasteurization with confidence. So when is this probability state? 180 day shelf life with confidence. You can whatever confidence level you want to. That has to be 95%. Since you are at for risk. And a technical decision by the business decision. So somebody in the business department you company with confidence they need to have that the search will be met. Could be that we want to make sure they are below a certain further detection level, and say that they say listeria free. What listeria free? What does it mean? It means you have fun of detecting listeria. It's specified in the regulation. The eye and the other level. It will have a certain detection level. What we want to use as a goal would be to be below the normal detection level with a high confidence level. And you can say 99.9, whatever you want. So we see here a pasteurization, a shelf life, a regulatory requirement. The operation I could make this going further. But we can see example is that the approach we're going to be using would be universal. The difference with the existing information available. So would have illicit values to be set randomly. As our quality assurance department is characterizing the raw material entering into the process, and they will be doing measurements, and you collect that information, and over a year you have lots of that. List, and you randomly sample from the list to have a sense of variability of the information. You could have that information casted using a probability distribution, could be normal distribution, a Poisson distribution, a curve distribution, any type of distribution could be recommended to describe the variability. Have something a little more complicated, often happens that you may measure something in a product, a load, a chemical concentration, a size, whatever you have to measure. There would be a detection level. So it could be that the one trying to measure, the analyzer you're trying to measure, is low, so that's not detected. So percentage of samples would be below detection level. So X reported as below detection level. The group of samples were above the detection, but below the quantifiable level. So you know it's present there, but you are not sure about the amount. Could be just using a probability distribution. So how we would handle this situation? So let's assume that we decided to use 1,000 of the resample. Percent of that 1,000 be the detection level. Some uniform distribution between 0 and or you can assume some linear increasing probability between 0 and some level. You could learn for the above detection but below a quantifiable level, and the rest would be described using distribution. If you can estimate a value, it's much better than just ignoring the first two types and just using an average from the measured value, which is so frequently done. Really ignoring that there are so many values below the detection level or quantifiable level and just rely on the measurement that gives you a number, is a gross overestimation of the load of that factor. An example, I've been going through so many slides. I'm anxious to show you how this is done. This very simple example. We're going to try to control the container film at a commercial speed when you process and plant. There's the 200 units per minute or multiple devices on the package line. It would be 1,000 units per minute. And a speed of 200 to 2,000 units per minute, I need to measure either the volume or heat that I'm putting in my container. And very easily, by the same time, you have to the speed at which you're trying to achieve this, and you consider that you're not weighing in an analytical lab situation, but the real condition of a processor machine and the vibrations and movement parts that are involved. Yeah. I give you a video so you could visualize how challenging it is to measure the film of the container. To give you a good sense of the petition, you actually show commercial example. So these are dried fruit pieces by a company in Oregon. They had a contract with a very large supermarket chain. They were looking for 100-gram pouches of this product. This was very important for this company, and a major expansion of their production capacity. They're very interested in ensuring that the buyer of the product will be satisfied and have an underweight amount of product in their pouch was to buy the product. A strong reputation for quality assurance. The guys were lying in the laboratories to ensure that the consumer will be getting the quality and quantity that they've been selling to them. So the person asked me for assistance. When you go to your line, adjust the fill station to what you think would be correct, and take samples from the pathogen line randomly, and at least weigh 25 samples very accurately in your analytical lab. Let me go show. So on the screen, measurement of 25 weight determined with a very accurate analytical lab data. These are not from the field station, but from the lab. Every single weight of the measurement is above 100 grams. First asking for help, he said that the company was losing money because they been product for free by using this field station setting. So it was in seeing how it should be reduced. The company will be making a few more profit from this product line. Okay. Go to the next tab here, and here we have again on the left side data. In two cells here, the mean and addition of the weight. So the mean was 103, and the ratio was 207. You see this line was doing a fairly good job at keeping the balance of product correct. Let me to the first strategy we tried was to see what the field value to every single pouch the gram, meaning the goal of 100 grams with percent confidence. So we can do that if this is the original minimum, the original distribution of our population. So this is the three value. when look at the statistic distribution, we'll find they look like this. This is the mean, and this will be generated using variation of that filling station. And here we generate a minimum value. So what if the value goes to minimum, which want to be graph. So we move this original minimum to a minimum 100 grams to meet the contract with 100% confidence. All we do is shift distribution to the right. In this case, we increase the mean field value. We adjust the filling station to a high field setting. So the minimum milligram. We have the original value of 103 as the mean and 207 as the standard deviation. One deviation because there is no reason that it will change when we do a minimum adjustment of the field weight. So when I come to the deviation, our mean value would be adjusted, so it would be modified. And of the station. And I know in detail, but there is a function in Excel called norm-IMV, which I'm putting there, which to generate distribution values if you have a uniformly distributed round number between 0 and 1. Is the first parameter of this function, H in there, and the next parameter of the mean and standard deviation. So this is my mean and this is my standard deviation. Okay. It's in time. And we see that the minimum of these 1,000 values is actually 96.3. Okay, 5 values, all of them were from 100. If you look at the simulation of this mean and standard deviation based on this 25 measurement, which is a good number of measurements, the minimum is actually below our target of 100 grams. The maximum, we don't care about that. We care about minimum and minimum. Okay? And the mean and standard deviation usually the values are very close to the original set. What we do, change this mean, so this minimum becomes 100. Do that in Excel to data analysis. Value of set cell, and we went to a value of 100. Then, like my target minimum, I will be 100 by okay, let's see that if we this contract with this very important customer with a confidence of meeting 100 grams, I will adjust the setting from 103 to 1. Okay. The problem with this approach is that extreme values are very difficult to predict. So this 100 minimum is the lowest value generated by this random distribution. and that is very difficult to achieve. So, illustration of that, here is another set of random numbers, and I replace those random numbers in the original, and now you can see that the minimum for the mean is up 100. So then I would have to redo my calculation. So you can actually go C. I change it. So I have to do this a little bit different. Go to trouble and have to change the initial value to get it out of trouble. Excel crash. So I have a monitor, I couldn't do anything. Sorry, my mistake. This random number that are generated by itself. I need to therefore giving variability. So okay. Now it used to be 107.6, and now the new set of random number, meaning a new generation of samples, my setting changed to 106.9. So the question will be, which one should you use, 106.9 or 107.6? And if I repeat, it will be going on and on forever. So when you make decision on extreme values like a minimum, it's not a good strategy. It's noisy. So to different strategies. Now to my PowerPoint. The different strategy. When I say that we want to have a contract with this company with the value met at 90%. So I go and negotiate with this company and say, look, we're going to try to meet the weight 20% confidence. And you get 99, but let's start with 90% to make example. What we're trying to do now, again, shifting the mean value and area of the desired field weight and the distribution of the new field weight setting 10%. So this little triangle here, 10%. So let's a table position and use the fraction, but this is the percentage I want. So 10%. Okay. And right now, I'm going to change the column of this. Then I want to be 100, then no 100.78. Okay? So I adjust the mean, so that the target 10% is 100 grams. So I'm going to the data. What is speed? Zero. Be 100 by okay, so we have decreased from 13.39 to 106.6. Only 80% confidence, 90% confidence, 10% probability of failure. So I want to say small. Now it's 0.1%. Now target is 96 in 100. So to increase my mean, so this becomes 100. So for analysis, goal sheet 100 by change. A setting of 106.4 would target with only 1% probability of failure. So we were pretty happy when we set up this approach to set the field setting. But then I said, stop. I mean, at 0.1%, I can try 0.01%, I can try 0.001%, or show you the same thing in my PowerPoint. So back. And this means field value further and further and further and further to the right side. And this tail here, as all as you want to. So I can go to 0.00000 whatever 1% and meet this desired field station, field weight of 100 grams. Where do we stop? Rational decision becomes with percentage of confidence, and you should stop your field setting. So this is where a risk analysis approach makes more sense. So set value, the risk of losing money is minimal. Losing money is something that all of us understand. Now we're going to decide the setting on two considerations. One, that our penalty on us for event we measure a weight of a pouch, and that is still the size field setting 100 grams. $100, $1,000, $10,000, what amount you put in the contract with this company, penalty the government sets on you if you miss a weight setting or claim amount of product in the pouch, penalty value that I need to have. And that I'm below the 100 gram setting, I'm all this is money paid off, but I'm not giving them the 100 grams. The product missing. And the amount above 100 and more. So I'm including product for the pouch, so the value. So add this amount. And this amount will find a cost of station. So the is negative, the value for C is negative, product missing is I favor. Right? So there's a possibility of finding a minimum. So how do you apply penalty for an underweight event? So every cost with less 100 grams meter out. The cost of the product, each bag, each pouch, is 1 cent per gram. And that the target is 100 grams per bag. Okay. So I'm it has two components. One and this number can be positive or negative. Remember, if it's over positive, it costs me money. If it's negative, it's saving me money. So this can be positive on this the cost of the product. So I need to use the to see. So weight in the pouch is about 100. And, in the 50, then out, which is this 10,000. If not, there's a penalty. It will be zero. But when the above 100, the risk cost is very like 19, they would by a penalty. So now the risk cost is very high. So the risk cost is very sensitive to penalty, as we could guess. I'm running the line as a set. So I'm in the original mean set 39. Now, this 1,000, the average would be $59,000 per 100 bags. So in other words, the per bag would be very quickly. I will and that for the weight because of the this penalty is so you can quickly I would be so to change the weight setting of the fill station. So unfortunately the function goes doesn't when you have risk cost with if calculation every time there's a logical function, basic does not work. I don't know of Excel, but if you are programming, you will not have it. So I'm going to go from 103 to 105. And you 6,000 to 7,000. So we're now 2,000. 1. Now it's okay. So this I'm talking about risk of 7 cents per bag. Say $1. So that could be affordable. Better. So it went up. Must be between 107 and 107. If you see the digits. Could be that 107.6 is best. If I keep goes up. It is 107.6. If I could have 106. This is a solution which minimizes the field setting risk. And we should have an objective to stop the adjustment. So when using the weight. It's a good keep going on and on, looking for a different setting, minimizing the from 0.1%, 0.001%, and we don't have to stop. In this, minimum to Excel, to power. Do an example. Every probability calculation in Excel, or you can implement them in any other programming language of your choice. Some more examples. Look at slide. So in this particular case, I'm looking at the spoilage of meat by the growth of this Lactobacillus sakei. What this will do is use an exopolysaccharide, so which is significantly high numbers of about 10 to the 6 per gram. Only have Torres reflecting the production of this exopolysaccharide. So have ever touch a meat that's been stored for a while, you will reach the skin on the surface as caused by this lactobacillus sakei. So we're going to use the process of this microorganism as an indicator of the shelf life of the product. To test the effect of time, called primary model. So primary model refers to the effect of time. Is the effect of time on this product described by this growth and 0. A certain time of adjustment of this packaging condition of your product. You're using some refrigeration, certainly some refrigeration of the meat, and probably using some modified atmosphere to and for this material will need to adjust to this new growth condition. Time, we assume it will begin to go exponentially in this maximum or shelf life maximum value of the bacillus present, and then on of time. It would be the TF value, which will be the sum of this time plus exponential time required to reach this minimum for shelf life value as lactobacillus, and estimated with this expression here above. First, we need to know is mu max and lambda. Into this equation, in these expressions, we do not see how to change the shelf life of the product. We need the condition of storage of this meat can be manipulated to live longer. The temperature, they show the modification of the atmosphere, maybe water activity, maybe addition of antimicrobial agent, etc. So we're going to just predict this lab, use the secondary model for this, the effects conditions. So here the effect of water activity. Have one. So your meat. This concentration of your two you're using in your packaging and storage. Before water activity minimum, you do all these other items are very expensive. So we can control the water activity, the temperature of CO2, and parameters. Here the variability only on field parameters, assuming constant temperature, constant water activity, and the package. And you get the shelf life of this meat will be between 200 and also this outlier here scale value of 950 hours. Here I know the shelf life is 5% confident. Go to the cumulative frequency and check with percent. Now I can see that for this condition, the shelf life of meat would be 250 hours, about days from the normal. I can estimation using the temperature, value CO2, and incorporate the addition of an antimicrobial agent. All things can be done following identical procedures with the let's scale a bit before we deduce the last example. Let's do on microbial safety goal, one of my favorite subjects. So, safety makes sense. What about zero microbial load, zero counts of a pathogen? All that it means is that it's non-detectable. And it's that we cannot. We have specific values. B equals 5, SB 12. The question, why going what? Or 12. In case here in Oregon, where electric field pressure scale up a pilot plant unit to commercial. And the company had to stop production and lost money invested in the pulsar electric field facility. So the decision of whether SD is equal 5 or 5.1 or 4.8 consequences. Okay, so we have probability of failure 1 in 10 to a 9 containers, and why not 2 or 10 to 9 or 2 and 10 to 10, and those things need to be thought a little bit more. We always talk about pathogens, most of the time in very generic terms. My question is, shouldn't we distinguish between microbial risk? Happening? For sure, there is a big difference between having gastrointestinal disorder, diarrhea, vomiting, versus septicemia, where it gets into your bloodstream and now to the heart because you're wrong. Should the amount of food consumed when this is processed. If I ask every day, certainly different the consuming a food item one day. I get it every day in my home, at least in mine. So why not incorporate consumption surveys into those easily generated? Every consumer knows that the supermarket is in intensity buying. Changes you make get forward. So how much the consumer is buying of each product. So getting consumption survey from supermarket data will be relatively easy to pay. A factor we should pay more attention is the dosage. Do all the same dose? Okay, and event for poisoning outbreak, the same data. So every time there's an outbreak of a given bacteria, the first the agents involved will do is try to obtain an estimate of the consumed. So did you eat, and they have an idea of how much was consumed, and also the number of persons present in food. They get a good estimate of the dose. And then many people were exposed to how many people ate at the same restaurant that caused the outbreak, for example. And fraction of people that have of the subject of the disease. Some of the events are increased, begin to have a good description of this curve. So those response curves are being generated, and for certain the number and quality of the data will continue to improve as our monitoring of food outbreaks. And last application is E. coli 0157 is served in apple. So there's a risk of unpasteurized use for children. The risk is serious because the death risk is a uremic syndrome, HUS. How we will show that the current regulation of heat pasteurization is only excessive processing. Response analysis will suggest that the is excessive of the evidence. So here, doing the same probabilistic engineering approach, the of the P of having HUS. So I have here risk for HUS. Get two groups of children, 2 to 5, the white column, and then black column. we get the ability to reach high value. Unacceptable. In the course of monitoring this for the government, for example, would include the need for intervention. No question, high risk of less disease by human unpasteurized issues. The factor that will make this so prevalent is that children have an only amount of apple juice in the countries that I visited. Apple juice is frequently given to children. So the government must correct in the need to impose regulations requiring the use in countries, UN regulations and all over the world. Use is not allowed to be sold. So, two processes in the recommended process conditions should be used to meet the 5 decimal reduction. The log reductions were sufficient, recommended in Wisconsin. So this is function, and they are in order to meet the 5 decimal reduction. After this process informed, they must use 68.1 degrees Celsius for seconds. The number of log reduction resulting from this process, the variability of our information on the 5 decimal reduction, which will be this point here, is really 3% of batches. So you have only a 1/3 probability, then at 95% confidence it should be required, you only are reaching 30%. We should have for 5 decimal reduction, if that's our intent. Meeting the 5 decimal reduction would be only 38%. If we look at New York, recommendation 71.4 seconds. So, probability is 20.8. So 1/5. Only batches of the so processes will need to be increased in severity, either temperature-wise or time-wise, or a combination of both. When we do perfectly, the probability of this HUS reaches very low value. It has a huge peak here in 10 to minus 16. So here we are doing our calculations, but they realize that Excel has a limitation. Every time that it reaches a small smaller than 16, it has a value of 0. So they can reach a center minus 16. Key here, minus 16, because in reality, this distribution curve should keep going into lower and lower values of probability. Now, probabilities are extremely low. They have such an event, an outbreak resulting from the threat used from New York. And while it has 20% probability of meeting the 5 decimal reduction, it's low. Therefore, studies suggest there is no need to reduction. That would have been much better. Would have been much better. Would have been to specify as a processing goal having the probability of having a disease. And design decimal reductions required to achieve the low probability of the disease. There's a little bit of time left for questions, so I open up and there will be vision now. We'll be looking at your questions and your talks, and if there's something that I need to answer. Thank you for your attention. Interested with you, interested in the subject matter, in a workshop on this subject matter, or in a short course at your institution, and please let me know how you can do it.
Thank you, Dr. Torres, for this nice presentation. We will now follow the questions and answers brief session. Anyone with questions for Dr. Torres, you may write them through the general chat right on WebEx, or there's also an icon as a raise hand, so that we can open up your microphone to ask Dr. Torres anything. So, please, questions for Dr. Torres?
If you have a question, please go ahead and I will translate for you. Meanwhile, I have one request, an additional request. This webinar, and really miss seeing your faces and interacting with you physically. And for I'd like to hear your suggestions on how to make webinars more effective. This is a new adventure for our organization. This is only our second webinar. And if there's any suggestion on how to make them more effective, they will be deeply appreciated by all of us. Not only because today, and we have in the future. For example, I can think of maybe sending you the presentation for the hour. Give you a chance to receive some applications on the topic of the conference. Those are just suggestions that occur to me.
Well, there are no questions. I do have a question. How often do people in the industry research, do they really use this type of tools, Monte Carlo or any other statistical simulations? If they are not really that used, what do you suggest to enhance this use of these statistical tools?
I rarely use, but just give a presentation. Company, I want to mention them, but they are used. And it's a problem. I think that we need to start with these tools in our educational programs. They need to be part of our food engineering and food process engineering courses. To something that we've been talking with Dr. Welty and other friends, we need to do workshops at professional meetings. Short at ISFE, for example, would be of value. People are not familiar on how to use them, but on how simple they are. I with the field packaging problem, really how it can be used in the use toys is very, very simple. And if you know how to use calculations in the regular way without specific considerations, you can do the same calculations using this. It's no different. We have a long way to go.
Thank you, Dr. Torres. If there are any other questions, we will finish today's webinar session. You remember, all of you, that the recorded session will be available for you within a few days, as well as all the files, in case you didn't have opportunity to download them down. So, everyone have a nice day, and thank you for attending this ISFE webinar session. Thank you, Dr. Torres.
Thank you for everybody at Montec for providing this opportunity. Thank you, the attendees.
Bye.